Thank you to Displate for supporting PBS.
One day, as part of a cooking class, a boy named Erasto Mpemba was given the assignment of making some ice cream. He boiled some milk, added some sugar, that's probably about enough. Then he poured that mixture into a container. Of course, he had to wait for it to cool before he could put it in the freezer. Who has time for that? I want ice cream. On that day in 1963, Mpemba was in a hurry too, so he put his hot ice cream mixture in the freezer while it was still hot. Now his classmates left theirs out on the counter to cool first before putting them in the freezer. But later, to everyone's surprise, even though everyone else's mixture had started at a lower temperature, Mpemba's ice cream mix froze first, faster than everyone else's. All of this happened at a secondary school in Tanzania when Mpemba was just 13 years old. When he found his oddly expeditiously frozen treat waiting for him the next day, he could have shrugged it off as some sort of fluke, a weird unexplained event. But he didn't. Instead, he asked why.
That question turned out to be a lot harder to answer than anyone expected. 60 years after the ice cream incident, physicists are still arguing about this phenomenon, now appropriately called the Mpemba effect. Maybe you've heard about this trick before, but what you probably don't know is how this strange observation, watching hot water freeze faster than cooler water, has begun to shake up very different corners of physics, from how we heat and cool machines to how we design materials, even quantum computing. Today, we're gonna dig into this deceivingly simple phenomenon to learn why taking the longer route can sometimes be faster. After I finish my ice cream. Hey smart people, Joe here. It turns out that 13-year-old Erasto Mpemba wasn't the first person to notice this. Scholars have been pointing out this weird effect for thousands of years. The first known reference came from Aristotle. Doesn't it always? It was all the way back in 350 BCE. He wrote this book called Meteorologica, in which he mentions how in certain places it was common practice to heat up water before freezing it. He points, for example, to ice fishermen in Pontus, in what's now Turkey. They would pour hot water on their rods because it freezes quicker, and then use that ice to hold them in place. Over the centuries, the effect was noted again and again by scholars. Here's one from Roger Bacon in the 13th century, or René Descartes in the 17th century. Lots of pretty smart people have been fascinated by this, and historians have since found numerous accounts of people around the world making the same claim. Hot water sometimes freezes faster than cooler water. But all this seems to go against our intuition about how heat works. So people have been pretty skeptical of claims like these, some even outright dismissing them as flawed experiments. When Mpemba asked his physics teacher why his hot ice cream froze first, he was told, "That is Mpemba's physics, not the universal physics." Skepticism is a good thing, of course. It's a necessary ingredient in science. But luckily, that didn't stop Mpemba. Years later, a physicist named Dennis Osborne visited his school, and Mpemba asked him the same question. Of course, his classmates laughed at him, but Osborne didn't. He went back to his lab and ran the experiment himself and got the same seemingly impossible result that Mpemba got. And they published it together, with Mpemba as first author. My name is Erasto Mpemba, and I'm going to tell you about my discovery, which was due to misusing a refrigerator. Let's take a second to appreciate how weird this actually is. When you freeze a cup of water, it cools continuously from room temperature down to freezing. If you start hotter, you've just got farther to travel before getting to freezing. So it should always take longer, right? This was captured in math by Isaac Newton in his Law of Cooling from 1701. It describes how things change temperature continuously. Compared to a room temperature glass, a hotter glass of water will drop in temperature faster at first, but then it'll just trail behind the other glass as they keep on cooling. I mean, that makes sense, right? Picture two curiously handsome runners racing to a finish line. One starts closer to the line, the other one starts one way back here. Obviously the one that starts closer to the finish line wins, right? Well, that's not always the case. Sometimes the runner who starts farther back crosses the finish line first, but only if he runs the race in a very certain way. That's the Mpemba effect. It's actually not hard to show that hot water can freeze really fast. On a super cold day, throw some boiling water into the air and it'll instantly freeze into these beautiful icy rainbow shapes. If you try that with lukewarm water, just get cold rain. But it has turned out to be incredibly challenging to demonstrate the Mpemba effect rigorously and repeatedly in the lab. In the decades after Mpemba and Osborne published their paper, physicists had attempted to replicate the effect, with honestly pretty mixed results. I mean, some studies seemed to replicate the findings, but others directly contradicted them. Now, there are two big reasons for this controversy. One reason is that these experiments are really tough to control perfectly. Like, whenever you compare when two liquids freeze, what tips that balance to one or the other can be so many things. The shape of the container, dissolved gases, how smooth or rough the surface is, or if something disrupts a supercooled liquid, because even tiny ice crystals can start a chain reaction of freezing. There's an absurd number of variables to control. The second reason is that water itself is very weird. It's actually most dense at 4 degrees Celsius, just above freezing. So as it cools, the coldest layer sinks and warmer water rises to the surface, where it evaporates faster. Once ice does actually start forming, those crystals float and insulate the water underneath, slowing the heat loss back down. Water is just surprisingly strange stuff. And for that matter, I mean, what does freezing even mean? Is it when the first ice crystal forms? Or when the average temperature hits 0? When it's fully solid? Different labs have used different definitions and gotten different answers. This is tricky stuff. So maybe the Mpemba effect happens just because water is uniquely weird, right? Well, not quite. Over the last few decades, that exact same signature effect, starting hotter and getting to frozen faster, keeps showing up in materials that they have nothing to do with water, which means that whatever's going on is bigger than just one strange liquid. Take these molecules, for example. Polylactic acid, or PLA. It's what many compostable cups are made of. And if you got a 3D printer, you've almost certainly used this stuff. But to form it, you have to get the molecules to crystallize. They lock into an ordered structure, which is sort of like freezing. And guess how you can get them to freeze faster? By heating them up first. But it gets even weirder than that. The effect doesn't just apply to temperature either. You can find a magnetic Mpemba effect too. If you look at the magnetic field of certain materials, you'll find that objects with a stronger magnetic field can be demagnetized faster. Again, winning the race by starting farther from the finish line. It seems like the Mpemba effect isn't some one-off quirk. It's a real feature of nature. Now, the thing that they all have in common, the more extreme it is where you start, the faster you can find your way back to equilibrium. A state where everything is settled and stable, done changing. You see, nature loves equilibrium. Leave out a cup of ice in a warm room, and eventually it melts. It settles at the same temperature as the room. A leaf falls onto the ground, and eventually it'll decompose and become indistinguishable with the soil. Everything, given enough time, ultimately seeks out sameness. Why does the world crave equilibrium? Well, it's simple statistics, really. Basically, there's just many more ways for things to be randomly mixed up than to stay clumped together. The lukewarm water is vastly more probable than an ice cube. Mixed up soil is more probable than an intact leaf. So what does this have to do with Mpemba's ice cream experiment? Well, inside of a freezer, the equilibrium state is, well, frozen solid. Both the hot and cold cup of water are racing to that finish line. The question is, how does the hot cup get there first if the cold cup has a head start? Does it somehow want it more? It turns out, well, sort of, yes. See, scientists have worked out a mathematical explanation for this shortcut. They showed that the fastest path to equilibrium isn't always the most direct one, especially when systems start with more energy. Imagine firing a ball into a maze. The harder that you shoot it, the more that it can ricochet around and maybe find a path to the target. A system with more energy and more things inside jittering and moving in all sort of quantum atomic-y ways, they can explore more pathways to equilibrium, potentially finding faster shortcuts along the way. Picture the road to equilibrium as a downhill journey. For a ball that starts here, it'll roll sort of sluggishly to the finish. But for a ball that rolls from here at a higher energy starting point, it has more energy to carry it to the end faster. If there are intermediate valleys along the way, the faster ball might be able to find shortcuts to the lowest energy state. That's how it reaches equilibrium faster. One group of scientists tested the effect by building this energy landscape in real life. When they dropped tiny glass beads into this landscape, they could stop at this first energy hump, or they could roll through that first one to this more stable resting place. They found that the beads that started out hotter tended to find the lowest resting place faster, just like the math predicted. And it goes even smaller than that. Down at the scale of individual atoms, physicists have found a quantum version of the Mpemba effect too. Picture a row of trapped ions, kind of like tiny compass needles, all pointing the same way. That's a state of symmetry. Now tilt them out of alignment. If you just leave them alone, they'll eventually drift back into sync. But if you tilt them further out of alignment, sometimes they snap back into sync faster than ions that were only disturbed a little. Physicists confirmed this quantum Mpemba effect in the lab for the first time in 2024. And this isn't just a curiosity. Researchers have started using this exact effect to quickly reset the memory in quantum computers. It's sure starting to seem like this is all the same beast in different forms. From freezing ice cream to wiping out magnets to quantum alignments. Now across all these different materials and different scales, there's one consistent theme. The shortest route is not always the fastest one. And we still don't fully understand why the Mpemba effect happens in every case, but that hasn't stopped people from putting it to work. Physicists are already exploring Mpemba-inspired tricks to make cooling and heating systems more efficient, which not a huge surprise. But Mpemba is turning up in some much weirder places too, like improving the manufacturing of ceramic materials. Now, some very special ceramics have to be compressed really tightly to be formed. Instead of using a big squish machine, one group used the expansion of freezing ice to squeeze the material. And sure enough, they found that the freezing happened faster if they started with hot water. Thanks, Mpemba. Who knows where else Mpemba will show up? I mean, that's the beauty of discoveries like this. You start with this tiny little oddity, something that doesn't seem quite right. And if you keep poking, you might end up exposing a new way of looking at the world. In this case, the mystery comes from assuming that everything is close to equilibrium. Whether or not we realize it, much of our intuition about the world is built on that assumption. I mean, we imagine that the air in a room is exactly the same temperature everywhere. We assume that flipping a coin 100 times will land us exactly 50 heads or tails, or that the balls in a ball pit are randomly distributed by color. But if you think about it, the things that are far from equilibrium are often the most interesting. Take fire. If you leave it in an empty room, it'll eventually peter out and just blend in with the air. But if you keep feeding it oxygen and fuel, if you keep pushing it out of equilibrium, it can light up your room, even drive your engine. And you and I and all life as we know it, we're all out of equilibrium too. All the work that we do in the world is only possible because we draw energy from the sun and from our food to constantly push ourselves away from equilibrium. When we fall into equilibrium, we die. We decompose, and we just blend in with the soil, just like that leaf. Far from equilibrium is where all the exciting stuff happens. But it's also where our intuition about the world kind of goes out the window. It's where nature can play all sorts of surprising tricks on us, like the origin of life, or earthquakes, or the Mpemba effect. This story is a wonderful reminder of the power of questioning the world around us, even things as trivial as a bowl of ice cream. You never know what it will turn up. New questions? Faulty assumptions, deep insights just hiding in plain sight. I think Mpemba and Osborne put it best in their very first paper about this effect. No question should be ridiculed. Everyday events are seldom as simple as they seem. Or, in other words, stay curious. Hey, before you go, we are really excited to tell you that the team over at PBS Eons just finished an amazing new TV show, and it's available now. Eons, Life and Death on Pangea, has everything you love about the YouTube show and way more. The series tells the ultimate story of the supercontinent Pangea during the Permian period. It was a time of massive geologic upheaval, full of incredible creatures, which all culminates in the greatest mass extinction in the planet's history. Check out the link in the description to watch.
Thank you to Displate for supporting PBS. Displate posters are vibrant, high-resolution metal prints with millions of images of space, nature, movies, shows, and more. If you love space exploration, Displate has real images from NASA, scientifically accurate diagrams, and celebrations of our most advanced telescopes. And they offer high-resolution digital representations of the cosmos, like Webb's Pillars of Creation. If you're interested in displaying images from your favorite movies and shows, they have posters from all genres, including anime or popular properties like Marvel, Star Wars, Lord of the Rings, or Warhammer. Each one attaches with a magnet kit that's included. No drilling, no holes, which works for owners or renters. If you want to switch it up, the magnets work with any of Displate's 2 million plus artworks. And with custom Displate, you can upload a photo, artwork, or graphic to turn most any image into a premium metal poster, whether it's for yourself or as a gift. Now, right now, you can get up to 33% off depending on how many you order using the code BeSmart. There are details and a link in the description, or scan the QR code to explore more.
And thank you to everyone who supports this show on Patreon, including these fine people at our top tier. High quality science communication and educational videos like this one take a lot to make. We very literally could not do it without the support of our patrons. If you would like to see more of this in the world, help us support this show and getting great science out to the universe, you can check out the link down in the description. We'll see you in the next video. Sorry, Carl, I win. I don't need to eat more ice cream at the end.
Rolling?